In this video here, we're going to take a look at exam revision for linear transformations. So as you can see then, this will cover the following topics here. So we start with transformations in 2 dimensions. We then have reflections and rotations. We have enlargements and stretches. We also have successive transformations here, followed by transformations in 3 dimensions. And then finally here to finish with, we have the inverse of a linear transformation. So as always here, what I'd recommend then is that you pause the video and have a quick look at the questions as they appear, and then just double check that your solution matches what we get on the screen. So that should give us everything that we need here to get started. Let's begin now with question 1. All right, so let's just get started then with question 1 here. Now, all things considered, I do think that question 1 here is a pretty straightforward question, and hopefully for many of you watching this video, you'll share that opinion. But anyway, let's just work through it together, and hopefully you do arrive at the same solutions, right? So what I've got here is this 2x2 matrix P. So the matrix P is 4, 0, 0, 2. Now for the first part of this question, then part A, all we want to do here is just describe fully the transformation represented by this matrix here, the matrix P, right? So let's just start part A then at the very top here. So for this matrix here, what you need to recognize then is we have a matrix of the form A, 0, 0, B, right? And if we have a matrix of that form, so A, 0, 0, B, then what we have here is a stretch, right? So what I've got here is a stretch by a scale factor of A parallel to the x-axis. So this value here is A. Then we also have a stretch by a scale factor of B parallel to the y-axis, right? So adapting that to the context of this matrix here, right? What we've got then is, let's write this down in full then. So we have a stretch. So we have a stretch by a scale factor. Of 4 parallel to the x-axis. So parallel to the x-axis here. And we also have then a stretch by a scale factor of 2 parallel to the y-axis, right? And you do need to write both of these down here. Obviously, you can't write down this one. So we're also stretching this by a scale factor of 2 parallel to the y-axis, right? So we also have, and we have a stretch. So we have a stretch by a scale factor of 2 parallel to the y-axis. Okay, and there we go then. So hopefully nice and straightforward, right? Just the 2 points here, and that we have a stretch by a scale factor of 4 parallel to the x-axis. And then we also have a stretch by a scale factor of 2 parallel to the y-axis. There we go then. Good stuff. That is the solution to part A. Now for the next part of this question then, what we're told here is a 2D shape with an area of A is transformed using the transformation represented by the matrix P. So again, that's this matrix here. So for part B then, it just says, given that the image of the shape has area 56, find the value of A. Right, so where do we begin here with part B? Well, again, this is pretty straightforward, right? Basically, what you need to consider here is the area scale factor, right? Now, don't forget then, if you have a matrix such as this one here, so this 2x2 matrix here, then the determinant of this 2x2 matrix here gives us the area scale factor, right? So if I know the area before, or in this case here, the area after, then we can find the opposite, right? So in this case here, because I've got the area after, by using the area scale factor here, in other words, the determinant of this matrix P here, then we can find the original area, right? The area of this 2D shape here, okay? So let's just start by finding the determinant, the determinant of this 2x2 matrix here. Now this is just a 2x2 matrix, right? And as we can see here, this diagonal is just 0. So calculating the determinant here should be really quite straightforward. I'm hoping anyway. So for det P then, here, we're finding the determinant of a 2x2 matrix. So normally what we do here is 4 times 2. So we do these elements here multiplied together, and we subtract the product of these elements here. But again, these are just zeros, right? So we're just going to subtract 0. So basically, the determinant here, I can't speak. The determinant of p here is just simply 4 times 2, which is just 8, right? So we just get 8 there. Perfect. Okay. So det p then is equal to 8. And this value here for the determinant of p, that is the area scale factor. So just make a note here, actually. The area scale factor. So the area scale factor is this value, right? So the area scale factor is 8. Okay. And because we know then the area of the image of the shape here, so the area for the image of the shape here is 56, then obviously I want to go backwards here. All we're going to do then is take the area here for the new shape and divide that by the area scale factor, right? So therefore then, the area here, A, so area A here is equal to 56 divided by 8 here, the area scale factor, and 56 over 8 then, hopefully nice and straightforward here, is just simply 7, right? So what that means then is the value of A here is just simply 7. So therefore A is equal to 7. So in other words here, the area of the original 2D shape here is just simply 7 units squared, right? And then by transforming it using this transformation here, the image of the shape here has an area of 56, right? And there we go then. So as I already mentioned here, we just need to find the value of A. There we go. Bosh, good stuff. That gives us the solution to question 1. So moving on to the next question here, let's have a go then at question 2. Now for question 2 then, what we've got here is the transformation W. So the transformation W, represented by the 2 by 2 matrix Q, is a reflection in the x-axis. So all we want to do here is just write down the matrix Q. Now again, this is just one of those things that you do need to recognize and be familiar with. So basically, let's just do this underneath them. So for part A here, we want to write down the matrix Q, where the matrix Q is a reflection in the x-axis. So basically what we're saying here is the point xy. So the point xy here will map to x minus y, right? Because it's a reflection in the x-axis. So xy will map to x minus y. So in this case here, we would normally start with 1, 0, 0, 1, right? However, if this is going to map to x minus y, then the matrix Q here is just going to simply be, so therefore the matrix Q here is equal to, so I get 1, 0, 0, and now this 1 here that we would normally write down is now minus 1, right? Just like that, okay? And there we go then. So again, you either just kind of learn that and kind of, commit to memorizing that result, or just kind of think about it in this way here. So xy maps to x minus y. So in that case here, the matrix Q is just simply 1, 0, 0, minus 1, okay? And there we go then. So hopefully, nice and easy there for part A. Let's just have a go then at part B here. I'll just do this underneath them. So for part B here, it just says the points A, B, and C are given as minus 2, 0, 0, 2, and 2, 4, respectively. So using matrix multiplication here, we want to find the coordinates of the image of these points under the transformation described by Q. So it gives you a big clue here, right? By using matrix multiplication. So basically what I need to do here is take these points and multiply those by this matrix here, right? And once we do that, that would give us the image of the points under the transformation here described by Q, right? In other words, a reflection in the x-axis. So there's 2 ways to do this. So basically what you can do here is just take each point individually, multiply that with the matrix Q here. That's fine. Alternatively, what you can do here, and this will save you quite a bit of time in the exam, is to take these 3 points here and write these as a 2 by 3 matrix and multiply that with the matrix Q. So I'll show you what that looks like then. So using matrix multiplication here, we take the matrix Q. So we get 1, 0, 0, minus 1, just like that, right? And I multiply this here with the the following 2 by 3 matrix here. So we're going to take these 3 points here, right? So minus 2, 0, 0, 2, and 2, 4. So each point here, I write that as a column of my 2 by 3 matrix. So for the first column here, I've got minus 2, 0. So minus 2, 0, just like that. For the next point here, again, I write this as a column here. That is 0, 2, just like that. And then finally, for the very last column here, we get 2, 4, right? So we get 2, 4, just like that. That is supposed to be a 2 and not a 1. It's a bit suspicious looking. In fact, it's that bad. I'm going to quickly redo it. Apologies. My handwriting is shocking. 2, 4, there we go. That's much better. So at this point here, you can do this by hand if you really want to, but I wouldn't recommend it. Just use a calculator, right? That is the whole point of using your calculator here in these exams. You know, there's no variables given within these matrices here, so you don't need to do this by hand. Just grab a calculator, throw it in, and press enter. So what you should get here then is also a 2 by 3 matrix, right? And each column then of the 2 by 3 matrix gives you a point, or the coordinates here of the image of the points, right, I should say. So again, what I'll do here is I'll give you the answer and then I'll try and explain it as I go. So what we get here for the first column is minus 2, 0. So basically, what we're saying then is the image of this point here, A, maps to this point here, minus 2, 0. As you can see, then it doesn't change, which should kind of make sense given that my y coordinate here is just 0. So I wouldn't expect any kind of effect here or any change. We just get minus 2, 0. Then for the next column here, what we then get is 0, minus 2. And then finally, for the very last column here, we get 2, minus 4. Now, you're probably looking at this and thinking, well, that all seems quite obvious given that, you know, minus 2, 0 maps to minus 2, 0. 0, 2 maps to 0, minus 2. And then 2, 4 maps to 2, minus 4. Surely that should just be the case, right? And yes, that is true, but obviously we do need to show this here by using matrix multiplication as the question asks for, right? And then finally, to finish with here, we can't just really give the answer like this. We do need to state the coordinates here of the image of these points under this transformation here, right, described by the matrix Q. So therefore then, the image of A here, the way that we denote this here is A with the little dash notation, so A prime here, that is equal to, so we get minus 2, 0, so minus 2, 0. For the image of B then, so again, B with a little dash here, so B prime, that is 0, minus 2, 0, minus 2. And then finally here for the image of C, C dash then is equal to 2, minus 4. 2, minus 4 there. Perfect. And there we go then. So that is the image of A, the image of B, and the image of C. Good stuff. So that gives us the solution there to question 2. And then finally, to finish with here, we have the very last question, question 3. Now, as we can see then, for the very last question here, question 3, we're kind of mixing 2 different parts to linear transformations together here. So what we've got then is a transformation here, or a linear transformation in 3D space here under this matrix M, right, as we can see here. And I'm hoping that's quite obvious. This is a 3 by 3 matrix. If you don't recognize this as a 3 by 3 matrix, you're probably on the wrong video. And then what we've also got here, right, is inverse matrices, and clearly from that then, inverse transformations. So let's just get started with part A then. So as we already mentioned, then we have the matrix M here. So 1, 1, 0, 0, 1, minus 1, and 1, 2, 1. Now the point ABC maps to the point 4, 0, 2 under the matrix M. So all we want to do here is just find the inverse of M, right? So M to the minus 1 here. Now, there's 2 ways to do this. You can do this by hand, which I wouldn't recommend for this question here. Alternatively, and this is the way that I would recommend doing this here, is to just use a calculator, right? The reason that I don't recommend doing this by hand here is because this matrix here is, you know, each element is numerical, right? There's no variables here, such as A, B, C, so on and so on. So I don't need to worry about anything like that. In other words, basically, I can just put this into my calculator here. And the way that these questions are written is basically with the expectation that the student will just use a calculator. So basically, if you don't have a calculator that can do that, then there's kind of no kind of like magic trick to this. Basically, just go and grab a calculator that can do this. Don't waste time doing this by hand. It is a massive waste of time, right? Anyway, as I've just said then, all we're going to do here is just use a calculator. So using a calculator here. So using a calculator. So all we need to do here then is just throw the matrix M into our calculator and then just find the inverse of the matrix M, right? So just put M to the -1 into your calculator, and that should give you the inverse of the matrix M here. So if you do this correctly then, and using a calculator, what you should obtain here then is the following. So M to the -1 is equal to the following. Now clearly, our result here will also be a 3 by 3 matrix. So what do we get then? So I get 3 over 2. I get -1 over 2. -1 over 2 again. I get -1 over 2. I get 1 over 2. 1 over 2. There's quite a lot of 1 over 2s here. -1 over 2 again. I've also got another -1 over 2 here. And then finally, for the bottom right element here, again, 1 over 2. So not the most creative of inverse matrices here. But there we go then. So that is M to the -1 there, or the inverse of the matrix M. So that should hopefully be nice and straightforward here. As I said then, please don't do this by hand. Just use a calculator. Okay. And there we go then. So that gives the solution to part A. Now for part B then, as a follow on here, and it says hence or otherwise. So straight away, that would suggest then that the answer from part A here will be helpful in answering part B. So hence or otherwise, find the exact values of A, B, and C here. So basically what's happening here then is we take the matrix M and we're timesing that by ABC here. Okay. And under this transformation then M, that maps to this point here, 4, 0, 2. So if we put that all together then, what's happening here is M, which is 1, 1, 0, 0, 1, -1, 1, 2, 1. Let's quickly jot that down here. So 1, 1, 0, 0, 1, -1, and then 1, 2, 1. We take that matrix there, so that's the matrix M, right? We then times that by ABC. That's A, B, C. And when we multiply these together, we obtain 4, 0, 2, right? That's the result there. 4, 0, 2. So by using this inverse matrix here, we can easily find ABC, right? So therefore then, ABC here is equal to the inverse of M, so that's this matrix here, times by 4, 0, 2, and that would give us ABC. So what I've got here then is 3 over 2, -1 over 2. I apologize, it's a little bit tedious writing this down each and every time. We'll need to do it a few times. So -1 over 2, -1 over 2 again, 1 over 2, 1 over 2 again, -1 over 2, -1 over 2 again, and then finally 1 over 2. Perfect. Good stuff. So that's the inverse of M there. And then we times it by this matrix here, 4, 0, 2. 4, 0, 2, just like that. And again, just use a calculator here. You don't need to do this matrix multiplication by hand. It is not necessary, and I wouldn't recommend doing it. It's just a waste of time, basically. So again, just throw this into your calculator. And if you do this correctly, then what you should find here is we get 5, -1, and -1 there. Okay. So don't just leave your answer like this here. Do state the exact values of A, B, and C here. So A is 5, B is -1, and C is also -1, right? So therefore then A here is 5, B is equal to -1, and C is also equal to -1. Perfect. Okay. And there we go then. So that gives the exact values of A, B, and C. And that gives the solution to part B and the solution to the very last question here, question 3. And that brings us to the end then of this video here on exam revision for linear transformations.